Hello and welcome to chapter 12, which is on thermodynamics. Thermodynamics is one of those fields that is very sticky and very difficult to understand and has a tendency to literally drive the people that study it insane. But it is also probably the field that most brought to light the 19th century and industrialization. So it is, and gave way eventually to quantum mechanics. So it is something that we do want to study. And what I'm going to do is I'm going to go over some of the fundamental postulates I'm going to go over some of the fundamental postulates as uh, quickly as possible, and then also just go over some of the uh, or the word's escaping me. Uh, some of the applications of thermodynamics based on uh, what we know and what we're going to learn. So thermodynamics is based on three laws of thermodynamics, and the zeroth law, which was discovered after the first two, but was so obvious that it was added to be before the first two laws of thermodynamics, was that if two systems A and B, so if you have two systems that are in thermal equilibrium with each other, where thermal equilibrium means that they're at the same temperature, so that when you place them next to each other, they're not going to transfer any heat because they're at the same temperature. And A and B, so this is A, this is B, and then B is at thermal equilibrium with the third system, C. So if B and C are also at thermal equilibrium, then A and C are going to be in thermal equilibrium as well, which is just like the mathematical property that if one thing equals another thing, and that other thing equals a third thing, then the first thing equals the third thing. So that's the zeroth law of thermodynamics, and it tells you a little bit about what we mean by thermal equilibrium. But when it comes to actually doing calculations and doing work with a bit of a pun there, with thermodynamics, we need to talk about pressure and the ideal gas law. So something that we tend to focus on instead of force for fluids like water or a gas is pressure, because force can be applied over a large area. And looking at the force that's applied over, say, the entire bottom of the ocean doesn't tell you much about the force that's going to be applied to your submarine if you're at the bottom of the ocean. What does tell you about the force that's going to be applied to your little submarine is the pressure, which is the force per unit area. So the force divided by the area that it's acting over. And that's going to tell you more accurately what type of conditions you can look at if you're just looking at one area, no pun intended, of the system. So if you're just looking at the hull of a submarine, then the force that's acting on it is going to just be the pressure at that point over the entire area of the submarine, rather than, or the pressure around the area of the submarine times the area of the submarine, rather than the entire force that's acting on the bottom of the ocean, which is going to be significantly larger because compared to the bottom of the ocean, what you're looking at isn't very important. What isn't very large. So pressure is useful in that way. So that's going to be something that we talk about when we talk about fluids. But for now, pressure is also something that we talk about when we talk about air, which is that the pressure is how much force is, if you have a balloon, then the air pressure inside of it is going to be how much force is distributed over the area of the balloons. Or if you have a tire, how much force is distributed over the surface area of the tire. So that is useful for the same ways and for the same reasons, and tells us what the force is like at a particular area, rather than the overall force of all of the air in the universe, or on the force of the on the Earth. So what pressure is determined by is the ideal gas law. So pressure times the volume is equal to the number of particles times some constant times the temperature, which you don't need to, like I said, this is a non-algebra based class, so you don't need to memorize this. All you need to know is that pressure and volume go up with temperature when the other is held constant. So if volume is held constant and you increase the temperature, then the pressure is going to go up. So if you have a solid surface and you increase the temperature, then the pressure inside the surface goes up, which is also how pressure cookers work in the opposite direction, where you have a fixed volume, but you increase the pressure so that the temperature goes up. And then in the opposite way, if the pressure is held constant, such as in a balloon where the pressure is going to be the same inside and outside, or inside and outside the balloon, then as temperature or the number of particles, which is in this equation, go up, then the volume goes up. So this pressure and this volume, where volume is the amount of space that's taken up by the balloon or the pressure cooker or whatever container you're looking at, when this pressure is applied to change the volume of a system, this can cause there to be work done, because work is force applied over a distance. And then if you apply a force per area over an area times the distance, which is volume, then that's going to, and you change this volume. So you apply a force over the surface of the container and you change the volume of the container, then that means that the surface is doing work. So going on to the next law of thermodynamics, according to the book, the first law of thermodynamics states the change in internal energy of a closed system equals the net heat transfer into the system minus the net work done by the system, which is just another version of conservation of energy. So energy, which is the total internal energy, so the total thermal energy, kinetic energy, and potential energy, all of the types and of energy added together can only be changed if the system does work or if there's heat transferred into the system. So if there's heat transferred out of the system, then it loses energy. And if it does work, it loses energy. But if something does work on the system, So if something compresses the system or like smushes the system together so that it's doing work on the system and causing a smaller volume, then that means that it's going to gain energy, and if there's heat transferred into the system, that also means that it gains energy. So this conservation of energy is something that we see a lot in biological processes. So you you don't need to worry about the variables or the equations here. Q means heat, U means energy, and W means work. But basically, through photosynthesis, plants take solar energy, so thermal energy from the sun, and convert it into chemical energy, which is able to then do the work that the plants need to grow and to survive. And then the humans do the same thing with their metabolism, where they eat food and convert the chemical energy into heat and work, which is how we're able to survive. So this is a biological version of what we see or what we're talking about in this chapter, thermodynamics. And then the third law of the second law of thermodynamics is that the second law states that the total entropy of a system either increases or remains constant in any spontaneous process. It never decreases. So what we need to do here is we need to define what entropy is. And entropy can be defined mathematically as the heat divided by the temperature, or the change in heat of the system divided by the temperature that's taking place. But that's not very interesting to us. That's not very obvious what that means for this level of class. So the other way to define entropy is that entropy is just the total disorder of a system. So basically, in any spontaneous process, so anything randomly happening that doesn't have outside work being put into it, the system is always going to be more disordered. So if you knock a glass off a table, then that glass will fall and break into 100 different little pieces, and it's going to become less disordered. It's not going to have the same chemical bonds. It's going to be very hard to put back together, but you'll never see it happen that the glass will come up off the ground and jump onto the table and mend itself back together, which would be an decrease in entropy. So this basically means that there can't be any fully efficient workaround from transferring heat to transferring and to doing useful work. And it also means that as time goes on, the total entropy of the universe is always going to increase for any spontaneous process. Why that doesn't seem to be the case necessarily. So why we're able to see glass be made in the first place, or we're able to take a deck of disorganized cards and put them back into order, which would be less from going from a less ordered state to a more ordered state, is because somewhere in the world or somewhere in the universe, there's something providing that energy and taking up the increasing in entropy. So for biological processes, this is generally going to be the sun that's creating that's becoming more disordered as time goes on, even though it is causing there to be more ordered biological processes through photosynthesis or chemical processes that go together so life can survive and propagate, even though the universe as in general and the sun in particular is becoming more disordered as time goes on. And then the third law of thermodynamics, which they don't even touch on in the book, so I didn't put it in here, is just that as the temperature goes to absolute zero, if you'll remember what we were talking about in the last section or in the last chapter, as the temperature goes to absolute zero, the the entropy of a system goes to a constant number for any given system. It's always going to be a constant number, which also means through reasons that are kind of opaque and kind of confusing, so I'm not going to get into them, that you cannot reach absolute zero because it would take an infinite amount of heat in order to reach absolute zero, in the same way that you can't reach light speed because it would take an infinite amount of energy. So why do we care? We care because this has very, very useful and very, very obvious applications. So or not obvious, but very, very useful and utilized. So we use these applications a lot. The first of which is a heat engine, which uses a cyclical process to do work. So first off, I want you to look at the long skinny graph, or the long skinny graphic on this in this system, where you put energy into a piston, or you put energy into gas, that because you increase the heat of it, it expands and moves a piston, as you see in the first two graphics of this, or the first two drawings of the skinny graphic. So it expands and moves the piston, which does work such as moving a car or moving a train. And then as that heat moves from the cylinder, from the gas out into the surrounding area, as you see in the last section, the piston is pushed back into position. It's pushed back into its initial position as the temperature decreases, and it does some work. It does some work on the gas, but the work that it does on the gas is less than the work that the gas did on the piston in the first place. So there is some net work being done by the gas on the piston, which allows it to convert from thermal energy to mechanical energy. And then what you see is called a cyclical process. So if you look at the top right graphic, it's going to show you a more generalized version of that process where you have some reservoir with a high temperature that introduces heat into the piston, and some reservoir with a low temperature where the heat is taken out of the piston. And then the work that's done by the engine is going to be greater than the change of heat, or the work that's done by the engine is going to be equal to the heat that comes in minus the heat that goes out. So this is the process for all or all types of engines, starting, I think, with the steam engine in ancient Alexandria, which became really useful in the 19th century as we created steam engines and trains and cars, which relied on this process for more specific and more useful properties than what they were doing with it in ancient Alexandria, which was just running puppet shows, basically. And then in the opposite direction, you have heat pumps slash refrigerators, which are just heat engines running backwards, where you have a low temperature and you put in work to have the temperature from the low temperature move through the heat pump and into the higher reservoir, which is, if we're talking about a refrigerator, it goes through the heat pump and into the hotter temperature area, which is going to be your house. So you'll notice that refrigerators actually take work. You need to put in mechanical work or electrical work in order to run a refrigerator, because it takes out it does the opposite of what you expect from society, or from like last lecture's rules for heat transfer, where the heat goes from the colder material to the hotter material because you put in that work. And then you'll also notice when you're talking about refrigerators that they are putting out hot air because the temperature and the heat is moving from the colder material to the hotter material through the work done by this heat pump. So these are, I'm sure you'll agree, very, very useful inventions and kind of indispensable, but and then they come directly from physics. So this is one of those things where general and special relativity gave us GPS and really space age technology, but this is something that you can see in your day-to-day life and kind of understand where it's coming from without having to spend years studying it, just understanding how that pump works, how you take in heat in, it puts out work, and then heat goes out into a colder reservoir. So that's all that I have for this section. Thank you very much, and I'll see you again soon.